Okay, so you just click on it and then it
Yeah, it will freeze for a bit,
long.
and then it will, yeah, and then it will
And then
show up in the
okay,
bar.
I see it now.
Okay, so welcome to FEA workshop. We're going to be going over as much as we can cover, really, starting with like just simple, kind of very basic FEA stuff, and then hopefully we can get into some assemblies by the end of it. But if you don't know, FEA stands for Finite Element Analysis. And in this context, what it's used for is for calculating things like structural loads, temperature, like propagation through things. FEA is also technically a part of fluid simulation. And all it is breaking up a complex model such as this into very, very small parts, and then solving simpler equations for those parts, and then combining it together. So we'll get into how it does that, but basically it's just differential equations and matrices. So a lot of fun. So yeah, to start with any sort of simulation in SolidWorks, obviously you first need a part. So for our first part here, we're going to look at, I just have the simplified model of the Thrustplate from last year, so no lightning or anything like that. And once you have this part, there's some geometry modifications you might have to do, and we'll get into those, but really all you need to do is go into your simulation tab, open it up from the add-ins if you haven't, and you can click New Study. Bring up this little window. We have lots of options because I think we have like the full SolidWorks package as students. So static is generally what you're going to be working with when you start off. This just means that anything about, if you guys took material science, look at a stress strain curve. Initially, the stress strain curve is linear. So essentially what that means, so with the linear static simulation, it just uses only that slope of the stress strain curve and doesn't actually use anything past the yield point of the material. And then also static means that as the part deforms, it doesn't recalculate any of the interactions between the parts. So if you have a model that's going to deform a lot, like usually like a plastic thing, you'll want to do a nonlinear study, a nonlinear dynamics study. And yeah, and then you can get into more interesting interactions. But for us, mostly using like aluminum, you can get pretty good results from static simulation. Also, there's frequency, so you can get like resonant frequencies from different parts that you have and figure out if you're going to run into resonance issues. That's outside the scope, and all of this is actually outside the scope of this tutorial. SolidWorks also has some topology optimization where it will actually like remove sections if they're not being useful. And then a design study will change dimensions if the part doesn't need to be as big as it could be. So rather than like just taking out random parts, if, in kind of like an optimized way, it will actually like reduce the thickness or change the diameter of pins or something like that. Thermal just looks at heat propagation through materials. Buckling, not very useful here, but for like bars where that might be important, we'll look at buckling of bars. Fatigue study. Also, fatigue studies will simulate like cyclical loads, so you can know so you can try and estimate like what your part life is going to be. Again, not that important for us since our part life is pretty much 2 or 3 cycles that we actually have to worry about. And I mentioned nonlinear and linear dynamic. And then there are also some weirder things like drop testing, which essentially just simulates like what would happen if you drop this part. And pressure vessel design lets you better simulate the effects of pressure on your system. So with a static simulation, you can model stuff like pressure, but it's a little bit more difficult, a little bit less accurate. And then grayed out here is submodeling. If I had already solved something, I could then like take a slice of it, or take like a little section out of an area of interest and solve it again. So essentially like the little cross section would use the forces calculated for the larger model, but then I could get in more detail in some area if I wanted. So
Hey, Troy, for
yes.
the pressure vessel design, can you do that like from the inside out? Like a tank
Yeah,
or
yeah.
something?
That's what it's meant for, is like tanks
Okay.
and stuff like that. Making sure that they can hold pressure. I mean, hypothetically, you could also do like a submarine or something with it. I don't think there's much limitation in that area.
Okay.
But yeah, so that's a kind of quick overview of all of the simulation options available. Again, we're going to stick with static for this tutorial. This is just an intro. So you'll create your study. The window won't change much, but you get access to all of these new things up here. And so essentially, you can just go down the line on this side. And by the time you get to the end, you will have set up your simulation. And if you've done it correctly, you can run it and it will work great. So we'll start off with the actual part geometry itself. This one, you can, usually what you would do is set a material if you haven't already. So I've actually set it in the part definition, but if I hadn't done that, or if I wanted to try a different material, I could come in here and change what material I'm going to use. Next up is connections. So this would be if you have like multi-body parts or assemblies, you want to tell the software how those parts are going to interact. Again, this is just one part, so you don't really have to worry about it. Fixtures are going to be a big thing. So fixtures tell the software how different parts of a geometry can move. So you can apply a fixture to a face, you can apply a fixture to an edge, you can apply it to a vertex, of which I don't have any. And you can also apply fixtures to whole parts and just make them rigid fixed parts. If you had a multi-part file or an assembly. So there are a couple different options. If you click on Fixtures Advisors, it brings up this annoying window up here, which I don't like. It's just usually just gets in the way, so I usually ignore that. So fixed geometry is going to be probably the most commonly used one. What a fixed geometry does is it makes it so that the face or edge or whatever it is that you've selected cannot move, it cannot rotate. So it can't translate or rotate or scale at all. So it's essentially fixed in place. So if we were going to do this part, Thrustplate, this is going to be the face that is going to come into contact with the bottom of the tube. So we can assume that this is fixed in general, and we can click OK. There's also a roller and slider. Same thing, it doesn't let the face rotate or scale, but it does let it slide linearly. Applying a roller slider here could also have the same purpose as it being fixed, particularly because our only force is going to be straight up through the middle. But generally, I stick with fixed unless I have a good application for roller slider. And then hinged, a little bit more specialized, allows you to make hinges. And there are other ways to do this as well, but we're going to stick with fixed geometry on this little lip for now. So we've set up our fixture, and that's the only really fixture we have to worry about with this part. I assume you guys all know this is Thrustplate, so motor comes up the middle, pushes on this little ring here, and then the body tube slots into this, if you guys didn't know. But next, we're going to do our external loads. So again, a couple of options for what you can do. You can apply forces, torques, pressures. So like I said, with the pressure vessel, technically you can do it in static simulation. Apply gravity to parts, or all the parts usually, centrifugal force, bearing loads. There's a wide variety of stuff that you can add. Generally, force, torque, and maybe pressure are going to be your main ones. And then if you're looking at assemblies, you might want to take into account gravity. If you have like parts you're going to be changing that are hanging off each other, you don't want to have to go in and change the force every single time. So we're just going to apply a force on the bottom lip here. So what I've done here is In the actual model, I've done a split line. Just up in the commands, you can access that whenever. And that just splits this bottom face into two sections. So based on the geometry of the little like motor sleeve that comes into contact with this is going to be the area where the motor sleeve touches the thrust plate. So this is the area that we want to simulate the forces. If I hadn't done this.
Troy, is that just a regular circle you just drew on in a sketch on the bottom, or is that some like special type of circle?
This is literally just a sketch.
Just a circle that you okay.
Yep. And then you just do a split line command, which is probably somewhere up in this window, but I usually just search for it. So split line here. You can also split bodies, but that's a little bit more.
Is split line just to create different regions?
Yeah, it just splits your face into different sections. So split will split bodies into different bodies. Split line will split faces into two different faces. So let's say I wanted to have like an area around each of these bolts, whatever it is, like 3/8 inch, that like the size of the washer. If we were going to have loads on there, I would also just come in here and make a sketch. And then I could do a split line on that sketch and select the face. And there we go. We have a new face that we can do whatever we want with. But yeah. So the split line here just makes it so that we don't want to apply forces where there aren't forces. We don't want to have like the thrust plate is not being pushed up in this region by the force of the motor. It's just sitting there. So that would be an incorrect way to simulate those loads. So we'll just have a force here. Motor we used was 1200 newtons, but I'm going to do 1675 because that's the bigger motor, and I wasn't paying attention when I did all these studies, and I did that, so ignore that. But basically, this is just the max thrust of the motor. And you'll have to do, depending on what you're doing, you'll have to do some other calculations as far as like the forces that you're going to be getting or the moments you're going to be getting. That's really just basic physics for the most part. You can approximate those. So we'll do 1675 newtons. And so we've gotten on the list, we've got fixtures, we've got loads, and those are the two main things that you need to be able to run a study. You need some way to tell the software where the part is going to be in space and what's keeping it there. And you need to tell the software what the forces on the part actually are. Next down the list is a mesh. So I mentioned that FEA takes a complicated model like this and splits it into a bunch of smaller parts. And it does this by doing a mesh. So it creates a whole bunch of tetrahedrons, which are just like shapes with all the sides are triangles, 3D shapes with all the sides are triangles. And based on that mesh, then the actual solver can come through, and for each individual, I forget what it's called. Each little like tetrahedron.
Finite element?
Yeah, element, yeah, that's what it is. It will come in and solve the equations that define how the part actually, or how the material will respond to forces. So the mesh, we have a couple of options here. Generally, when you just start it up, it will just show this mesh density, and you can set this anywhere from super coarse to super fine. Generally, a more fine mesh is going to get you a better or more accurate result, but that is not always the case. You can also come down here. There are a couple of different mesh parameters. So a standard mesh just kind of, it pretty much just draws triangles and connects between them. This is your most basic sort of mesh. I don't know that you'll really be able to see any major difference between these on this part, but this mesh just keeps it pretty simple in how it makes the mesh. There's also a curvature base and then blended curvature base. So a curvature based mesh. So in a standard mesh, you define your maximum element size and your minimum, or sorry, this is your global size and your tolerance, how much that can be different. For the curvature-based mesh and blended curvature-based mesh, you define a maximum element size and minimum element size, and then you define a minimum number of elements in a circle and an element size gross ratio, which you really don't need to touch. So curvature-based meshes will be a little bit more accurate when you're looking at parts with generally small curvatures. So a curvature-based mesh will look at the curvature of the part that you're looking at, or the face or whatever it is, and it will scale the mesh based on that. So particularly the minimum number of elements in a circle, if you have a super small, like 0.001 inch fillet on one of these edges, it will try and cram a lot of elements in there. And then a blended curvature-based mesh will do the same thing, but in the flatter regions, it will make it bigger than, it will make the elements larger than what the curvature-based mesh will get you. So it can be a little bit more optimized if that's the kind of mesh setup you're looking for. So generally, it's a pretty good idea to run a blended curvature-based mesh, unless you get mesh errors, which we'll get into near to the end. You run it and you'll get a mesh. So this is what it looks like. Obviously, we just see the 2D. I think we get a 2D look at what the tetraedrons are, but these do extend into the part in 3 dimensions and go all the way through the part as well. So now that we have the mesh, we've gone down here, we have everything that we need to run the actual studies. So we'll run the study. This mesh is not the densest mesh, but it's also not like the finest mesh, so pretty quick to run. And then we get our result. So a little quirk of how FEA works, and it's more of a fun fact than anything. It only really matters once you get into making it, is FEA solves for the displacement of every element in your part. And then from that, then you can use material properties. So solving the displacement will look at stuff like the modulus of elasticity and stuff like that with your material. And then to get something like the stress or the strain of your material, it will just do some math there that's not necessarily related to what you would normally consider FEA. So that's a little bit of a fun fact about what FEA is. But the first thing that will pop up when you do a results window is your stress. So stress in this context is a von Mises stress, which is, so stress can have different directions and dimensions, obviously. So if you really wanted to look at like normal stress and normal stress in each direction, you have to have multiple plots. What von Mises stress does is it just takes all that stress and kind of averages it into a single number for stress. Excuse me. And that just makes it a little bit easier to analyze. So as you can see here, higher stresses are in red along the edge here, and lower stresses are in blue. So obviously in the middle of this part, there's very little bending. So the stresses are pretty low, you can see there. And yeah, so we'll get into a little bit how to analyze this and whether this is actually a good result in a second. But this is your general simulation result that you want to be looking at and trying to understand. Displacement is also useful. It just gives you how much each part is displaced. It's really good for like looking at your model and figuring out like, hey, does this make sense as something that would actually happen? So with the force applied on this bottom ring, that's the most displaced part, whereas the parts that are fixed have very little displacement. So that makes perfect sense. You can also come in here and define a whole bunch of other plots. The one we are really interested is going to be our factor of safety plot, which tells us how many times stronger the part is than what it needs to be to not fail. So if you look at this part, we're getting a minimum factor of safety of 6.4, which is quite good. just as a number, ignoring any of the actual analysis we might do on this part to figure out if this result makes sense. Generally, for like a general rule, might be like 3 factor safety for most parts. If you're doing aerospace, you can get into like 1.5, maybe 1.25, because you know, gotta save weight. And then like human rated stuff will have 5 or above factor of safety, or sorry, like industrial kind of like normal stuff you might find will have much higher factor of safety, is 5 or above, just because like someone like hangs on a TV or something, that's going to put like 5 times the amount of stress that your monitor arm would normally have, and you want to make sure that that's not going to kill anyone. So yeah, it really just depends what the application says. Yes.
So for factor of safety, when you say it's like, you know, how much stronger it is than the like actual failure point, it seemed like you didn't like input anything for like is that just based off the load that you apply, and then it just calculates like, is there like a maximum limit to the deflection or something, or does it just go until it breaks?
Yeah, okay. So for a linear static analysis, there are no like plastic effects. So what we're really looking at is the yield strength, not like the ultimate tensile strength or anything like that. And SolidWorks, yeah. Well, so SolidWorks is good because usually you can just leave it as automatic as the failure criterion. But I could go in here and change it to the maximum von Mises stress, maximum shear stress. I don't even know what this is, or the maximum normal stress. And if I wanted to do a really in-depth look. But for most parts that that newbies are going to be looking at, leaving it at automatic is perfectly fine. And it will tell you not necessarily what the lowest factor of safety is, though it will often do that, but what it has determined to be the most significant impactor, like how it thinks the part might fail. So if you're doing something that has a super low, some material that just can't handle like shear stress, it'll get shear stress, or let's say your normal stress in one axis was significantly different than another axis, then it might look at normal stresses in different axes. But in general, leaving it on automatic is fine. Then you don't have to worry about any of these other tabs.
The key thing though is that it just goes until it starts plastically deforming though.
Yeah, so you can actually take linear static models beyond their yield point. They just stop being accurate after that. So you can do like a simulation with that, and if you see it, then you'll have to go back and do a nonlinear study to actually figure out if it's going to deform like you think it will, and if it will fail due to that deformation. For the metal parts we're going to be working with, they have pretty high yield strengths. So
it's an issue if we're plastically deforming aluminum in our rocket.
Yeah, and yeah, if we were going to make parts out of like plastic, then we would be more concerned about the nonlinear dynamics of what's happening. But for the stuff we're making, static studies are perfectly acceptable. But yeah, so you might notice that this is all red. That's just because the scale usually gets a little messed up because it goes to the maximum value of factor of safety, which we saw earlier. There were some areas like in the middle that have basically no stress on them. So you can just come in here and set it to like 10. And then it's a little bit easier to see. This is mostly concentrated on this edge here. We'll talk about that in a second. But that's basically how any simulation is going to work. You just have to be careful whenever you're making simulations about setting things up right and making sure that your forces, like you haven't put in an extra 0, because then obviously that's not going to go well for you. And that's usually why I have people check your studies after you do them to make sure that, hey, yeah, this result makes sense and all that. But that's your basic FEA, I guess, flow. So you can see here, I did other studies, same kind of thing. It should be exactly the same, in fact, in here. Now, there are other things that you can also do that are kind of, will speed up your study. Obviously, this study didn't take that long to run because I had a pretty coarse mesh, but finer meshes studies can get to take a super long time. I had a study that kind of messed up, but still did it. But so it took like over an hour to solve, and it was only like halfway done. So there are a lot of points where you want to optimize your models and your simulations to make them run a little bit faster. And one of the really useful things that we working with circular rockets can do is take advantage of symmetry. So obviously it's a circular rocket. In general, a lot of these parts are going to be symmetrical or symmetric about 1 or 2 axes. So you can see here I have same part, but just cut in half. And same fixed load, same force, except now the force is divided by 2, because obviously only half the force is acting. And then up in this fixtures, if I go to advanced fixtures, there's an option to do a symmetry fixture. So essentially what that does is it just tells the software that this face has to deform in such a way that as if there was the rest of this on the other side of it. So it doesn't have to solve this whole extra half of the part, but it will still get a result that matches that. So all I did here was just kind of like make a half circle and do a cut in the actual model. But you can then get symmetrical results. And then you can also extend that to, as you might imagine, this is symmetrical about 2 axes. So we can just do a quarter of the model. And now this study was run with, look at displacement here between all of them. The study was run with the same mesh size for each, but obviously as we got into smaller components, it went a lot faster. And I can compare the results of the displacement between the models here. You can see 5.053 times 10 to the negative 2 millimeters for the full model, 5.035 for the quarter model, and 5.055 for the half model. So a little bit lower displacement as you get into the smaller sections, but also this is 0.0002 millimeters difference. So not something we really have to worry about. So we'll take advantage of stuff like symmetry a lot if we want to make our models run a little bit faster.
What computer components does SolidWorks use the most? Like
So
RAM,
SolidWorks
CPU,
will
GPU?
use RAM and CPU for your simulations. So
It's never enough RAM.
there's never enough RAM. I on that hour-long one I was talking about, I got up to 14 gigabytes of RAM used, so that was fun. But yeah, so the finite element method and the finite difference method are kind of annoying for computers in that you can't solve one without knowing, you can't solve like one section without knowing the results of the other sections. So what that means is that you can't take advantage of multi-core processors. Really, I mean, there are some like things you can do to take advantage of it, but for the most part, something like SolidWorks will benefit the most from single core performance. So your CPU core, I mean, it's changing a lot. I guess AMD is a lot better now, but Intel has generally been the single core performance king. So Intel CPUs will be a little bit faster than AMD CPUs because they have a lot of cores. Or like a Core 2 Duo will be faster than a Xeon because just can't take advantage of all those extra cores unless you're running multiple different simulations at a time. And then RAM, you can have that hour model again. I think I counted up to, or it said that it had like 4.6 million elements that it was solving for, which is a lot. I don't even know how many this has, not anywhere near that, probably below 100,000. But yeah, so you need a lot of RAM to store all the data about the elements, and you need a lot of single core CPU power to do these studies. Yeah, okay, so that's basic FEA analysis and basic optimization there with the symmetry. Pretty much everything I talk about in this workshop is going to actually be like multiple full semester classes to actually figure out how it all works. But we're just going to gloss over that because I don't know most of that either. So we're going to skip it. But something that is super important to know is how to know if your results are accurate. So I have this result here. I have my stress and I have my displacement. And you can sometimes say like, yeah, that makes sense. Like it should be pushed up in the middle. It should be solid on the sides. You could say that the stress kind of makes sense. Like this is where it's fixed. This is where it's not going to move. So there's just going to be a lot of stress on this point. But really, we want to ensure that this result mathematically is an accurate one. And what you're going to want to do for that is run a mesh independent study. And all that means is we have our mesh here. If I make this mesh half the size, it's going to take twice as long to run, but hypothetically it will be more accurate. So what we want to do is quantify how much more accurate making a smaller mesh will be, and then figure out based on that. First of all, you'll have accurate results, and then also important is you will be able to optimize your computing time, because obviously you don't want to have a super small mesh if you don't need it to get accurate results. So a mesh independent study, essentially what you do is you take your model, you create a mesh, and you start somewhere in the middle, and then you solve it, and it will give you some result. I don't know why. And it'll give you some result for like your stress, maybe you want to look at. And then do it and create your mesh, make it a little finer this time. Run it again, see how that changes. And as you do it, what you'll see is something called convergence, where if you look at a graph of the like mesh density versus the stress or whatever you're looking at to calculate, it will hopefully come to a asymptotic kind of line. And that will be great. So here, what I've done, well, actually, you can do that manually, like I just did there by adjusting the mesh and then like maybe writing down numbers and punching them into Excel or something. Or you can have Solidworks do that for you. So Solidworks has two options for being able to do that. If you come into the study properties over here, you can go into adaptive. There are two adaptive methods that you can use. Well, none, obviously just runs one study. H adaptive studies will do exactly what I just did manually earlier. It will start with whatever mesh you set it as, and then it will run that, and it will look at what the target accuracy is. It's not really important what this looks at, but look at the target accuracy and look at, and it will bias the results towards one thing or another. And if you're within the target accuracy, it'll say, good, you're all set, go to the races, whatever. If you're not, it will then make the mesh a little bit finer, and it will run it again. And then it will compare that result, and you can set the number of loops you want it to do. Maximum in a single run is 5, but let's say you do 5 loops and then your model still hasn't converged on a stress, then you can just click run again, and it will have saved the most fine mesh that it has, and then it will just run again from then. So then it will run that and optimize the mesh a little bit more. So it can take a while, but it's a little bit, it's really important to make sure that the size of the mesh isn't influencing the results of your study. So you can see here we've come back to Thrustplate model. This time we're using the plotted version. Same type of thing, fixed geometry on side, symmetry, or fixed geometry on the level lip, symmetry on sides. Force on the bottom this time, we're doing the actual value, which was 1200, and then divided by 4. 1200 newtons divided by 4. And we have I think we have a mesh for this. So this has actually already gone through the a few steps. I forget how many. It was like 4 steps of the H-adaptive method. And it's arrived at this mesh, which is going to take quite some time to load. In fact, I might have just crashed Solidworks, which would not be ideal, but well, we're waiting for that to load. So H-adaptive, like I said, changes the mesh size. There's also P-adaptive, and what P-adaptive does is, without getting too much into the math, because I don't really know what it is either, but what it will do is take this thing called a shape function, which is, there's a shape function for every element in your model. And that shape function is a polynomial of a certain order. Usually, in most cases, 2. Second order polynomial will pretty well describe it. There's the mesh there. And it will run the study, and it will look at the results of the study, and if they're within some parameter of interest, then it will stop the study and say your model has converged. And if it's not, it will change the order of the polynomial describing each element, depending on where the element is, to get a more accurate result. It's a little bit hand-wavy with the mathematics, but it works. Generally, I prefer to stick with an H-adaptive because I can actually see like what's going on with the model. Whereas P-adaptive, you can't really easily visualize it. There are ways to visualize it, but they're a little bit weird. But yeah, so generally I usually stick with H-adaptive. So this is the mesh that I arrived at after, it might have been like 5, I think, H-adaptive passes. So you can see it's super, super, super granular, especially in these areas here. We can pull up our convergence graph here. Like I said, so there's going to be the loop and then the value of the stress. You can see that this model is going exponential, which is not good. Like I said, we wanted this to converge to I guess I should have specified a horizontal asymptote. This not up down here is just because I stopped the study because it was taking a super long time to solve, as you might imagine, looking at that mesh. But so we've done everything right here. Hypothetically, we've done a mesh independent study. We're looking for the point where the mesh converges, and the mesh just is not converging. And this is obviously a super, super detailed, I think it just crashed. I don't know where it went, but you saw the mesh that was super detailed in a lot of areas. So why is the question? Why has that not converged? And what we're gonna look into is singularities in models. So I'm gonna go back to this part here because it's a little bit smaller. If I look at the stress here, you can see that it's pretty low stresses, like well below the actual yield strength of the part in most areas, anywhere like green and below. And then right along this edge, it gets super, super high stresses, which is where we're getting our lowest factor of safeties here, right on this edge. And we have to look at this result and say, like, does this make sense? Or is there something going wrong with the model or the math or the geometry that is making us get this weird result that doesn't make sense? And here, so there are 2 options when you have a small area like this where all the stress is concentrated. It will either be a singularity, which is not good, means your model won't converge, or will be a genuine stress concentration. So that might be like where you have a bolt going through and the bolt has a pretty low area of contact, but it's pulling really hard. So you'll get super high stresses there, but that makes sense. That is a genuine result. Whereas what's happening here is we have a stress singularity where the math that describes all these elements is breaking down at this 90-degree corner. And you're getting what will happen, like we saw with the convergence plot here, is rather than converging to a single stress value, your results will converge eventually to infinity as you make each of these elements smaller and smaller, which logically doesn't make sense. You're not going to have infinite stress. First of all, the infinite stress doesn't only make sense because if there was infinite stress, the part would yield well before that. And that's actually an area where you might want to do a nonlinear study, because nonlinear studies will take into account that plastic deformation rather than just assuming that the material has the same properties essentially no matter what the stress is on it. But really, when you have something like this where it doesn't converge, that's a pretty good indicator that you have a singularity. It doesn't have to be an outside edge like this. In fact, more often than not, it's an inside edge or like a crack in your model. If you have some weird geometry there, you'll get super concentrated stress that will never converge to any value. So we want to avoid that. So if we look at this simulation here, our factor of safety, it reports the minimum factor of safety to be 6.4, but that's a singularity, and really the actual factor of safety in the model is going to be contained somewhere else within the geometry. So the one I showed you earlier with the super fine mesh, I ran this a bunch of times. With the default mesh, I got a factor of safety of 4. With the fine mesh, I got 3.7. I changed the maximum mesh size to 0.05 inches, got a max of 3.3. And then I changed the local mesh size right at the area of interest to 0.03, super small, and I got a factor of safety of 1. So that is a really good, that will show you well that you have a singularity if your factor of safety just keeps on going down, especially something as dramatic as this. So how do we get rid of singularities in our model? There are a couple of ways to do it. Most commonly, what people will do is add fillets to the edges. And that's just because fillets offer a transition for the stress to run along, and then as long as you have a decent enough mesh density in those fillets, you will the singularity will disappear. You might need a super dense mesh to get it to work, but in general, it will. Another option, like I said, is to run a nonlinear study where the stress cannot reach infinity because the material will plastically deform before that. So it will take into account that, and then you won't get the singularities in your model. And then another option is to just ignore it and say, I, the engineer, I'm looking at this, and I know that this result does not make any sense. So we're just going to ignore it. And that's actually what I've decided to do with this model. So I tried the fillets, but this is a super small lip. So the fillet sizes we're talking about, it's still, they're like 0.02 or something radius. So it's still a singularity, just as a result of kind of how we fixtured this.
But this is what happened to the de Havilland comet.
Yeah. Well, yeah. So that was a stress concentration. Yeah. So that was a stress concentration. So that was an actual
same kind of shape.
Yeah. So that's kind of where the issue comes in identifying whether it's a stress concentration or a singularity, and that's where the convergence plots help out a lot in being able to determine that. Because stress concentration will eventually conserve, particularly once you get into a mesh like I had. But this one was just increasing exponentially. So that's a singularity rather than a concentration. So for actually solving, if I was going to just look at this part, this is how I'd probably do it. Just ignore that singularity in essence. So I have a factor of safety, it still reports, it's still a different geometry, but reports as 3.6. If I went lower, if I went smaller mesh sizes, that factor of safety would obviously keep decreasing. But something you can look at here is doing something called iso clipping. So It's the same factor safety plot, but I've turned on isoclipping, which essentially you can either remove anything below or above whatever value of interest you're going to say, you're going to specify. So here I have it only showing areas that have a factor of safety below 8. This is probably about the point where I might say that this has stopped being a singularity and is actually just a stress concentration. So singularities happen at a point, and they do affect the areas outside of it. But this is getting into a pretty large area of high stress that probably wouldn't necessarily only be caused by the singularity. I can like take it up to 12, and then you can actually see the other areas of stress. So right on the actual where the motor is contacting, you have some compressive and bending stresses here. So if I were to like put a value of factor of safety on this, I might say like 10. That's kind of where that starts to come into play. And that's kind of how you would look at it if you were just doing, like just analyzing this single model. And you can get some pretty good results. So in fact, this doesn't have a factor of safety of 3.6. It actually has a factor of safety close to like 9, 10. And yeah, so that's one way to deal with singularities. There's also another way to do it, which, let's think about what's causing this singularity here. It's because we have a fixed face here, a fixture that is fixed, which doesn't really make sense if you really think about it. I mean, we're going up against blue tube with some fiberglass around it. Aluminum is probably stronger than the blue tube, so the blue tube will deform a little bit, and maybe the aluminum will, and if we're using something like fiberglass, pure fiberglass, maybe the aluminum will deform a little bit because fiberglass is a lot stiffer than aluminum. It won't be perfectly rigid. There's also nothing really keeping this perfectly flat. So a lot of what's probably causing the singularity is a bending moment that is kind of phantom. It doesn't really exist in the actual model. And in reality, if this was being pushed up, the face would come at an angle a little bit. But our fixed geometry isn't allowing that. So we're getting super high concentrated stresses on both of these edges. So you could like get really into doing advanced fixtures and all of that and kind of try and avoid that. That would probably work for you, but it would take a super long time. A lot easier method to get around it is go with the idea of fixing your geometry kind of 1 degree outside of the area of interest that you want to study. And that's going to be a great way to get rid of singularities. Not entirely, because we're still going to be using a fixed geometry. So there's going to be some kind of weird interaction singularity there, most likely. But get rid of singularities in the area of interest that you want to look at. So here I have an actual model of kind of what the thrust plate is going to look like in the assembly. So we have our retention sleeve here, and we have a body tube. So here I have a little bit hand wavy, kind of approximated this. I've made the body tube material as steel because, like, let's say it's fiberglass, it's going to be stiffer than aluminum. But simulating composites is well outside my area of expertise, and it's quite complex to do. So having a stiff material like steel is probably a pretty good approximation for this case. And the fixtures now are applied at the top of the body tube. We're still using symmetry here. And the force is now applied instead of on the thrust plate itself. The force is applied on this retention sleeve. You'll notice I've changed the geometry a little bit. If you know what the retention sleeve looks like, it actually it continues down further and has a little ring where the motor pushes up against, which you could use, but in essence, you're just going to get a force coming up through this face where I've cut it off. And we don't really care about that weird geometry in there, and that's just going to cause even more singularities and be annoying. So cut off the model and make it a little bit simpler. And if I run this, I can actually do another. So with this, I did a age adaptive study. Put the target actually a little low because I was having some troubles converging, but anything above 95 will get you some pretty good results. And we can actually see our convergence graph where it does actually converge to a good value after 3-4 runs of it. And we can see our factor of safety here, just looking at, so you can come in here and do the graphs with just selected bodies. So we only care about the thrust plate. So we're only going to look at the thrust plate. But our factor of safety minimum is 7.5. You can come in here and do the ISO thing again, and you can see the factor of safety below. I probably have this set to like 8 or 9 or something. Is only in this areas where there's a lot of compressive force from the motor itself, which makes sense. So this part would probably most likely have a factor of safety of around 7.5 based on this simulation. So we kind of solved the problem of convergence, which is great. Again, you'll want to fixture and apply loads to your model as far away from the area of interest as you can, because then you'll avoid getting any singularities and stuff in that area. And yeah, so we can also quickly talk about doing assemblies. So obviously this is multi-part. Each of these has a material applied to it. And then the thing we skipped over when we were just doing a single part is our connections. So in this case, it's pretty simple. Whenever you have a model with multiple bodies or multiple parts, when you make a new, here, I can just make a new study in fact. When you make a new study, it will come in with this little folder for component contacts, and there will be a global contact definition. So this tells the software how all of the parts are, if they're touching, this is how they're going to interact. 3 options. First is no penetration, which means that the parts can't intersect with each other, which makes a lot of sense. There's also bonded, which is the default, which means that any faces that are touching are welded together, essentially almost thought of as the same part in terms of the solver. Not quite though, but that's going to be the default, and sometimes that'll be useful. And also allow penetration is somewhat less useful, but it has its applications everywhere. You want to leave this checked as global contact because this is how you want all the parts to interact. For this model, I would select no penetration since like here, this internal wall is contacting the outside wall of the thrust plate. Those aren't bonded together. There's nothing keeping those together, so we will not bond it on this. No penetration will make sure that this doesn't push up through the thrust plate or anything like that. And then you can get into other connections. So a contact set is where you can like define contacts between faces. So let's say I wanted a bonded contact on everything except those 2 faces. I would go in and set this contact set with those 2 faces to be no penetration. And then anything I don't set a contact set on will just inherit the global contact, which is going to be no, which would just be bonded in that case. And yeah, so connections again aren't overly complicated. We'll get into a little bit more of these, which are actual like mechanical kind of methods of connection, which it can also solve for. So rather than like having to model a whole bolt and model all the contacts between the faces and the forces on the bolt, it will do a simplification, which will get you very good results without having to deal with all of that, depending on your use case. And yeah, I showed you this actually converges, which is great. Shows that the model actually works. So we've done a lot. I've talked a lot. Any questions about what's going on? Things I glossed over, anything? Okay, so we can also move on to our next model. This is going to be a assembly that we're going to analyze. So whereas the previous assembly was, we were just really looking at one part, we were just kind of using the assembly to get some results for it. This assembly is going to, we're going to want to look at how all of these models interact with each other, and that's going to be our area of interest for our study. So again, it's a very similar setup process. You just make a new study, come in here. Our global contact is going to be defined, which we're going to set to no penetration. Our fixtures are going to be here. On this case, we have some split faces. This is where the washers for the U-bolt are going to be. So the U-bolt would come out through the top here, be attached to the parachute. So this area we can assume to be fixed. And then our forces are going to be, that shouldn't be per item actually, it should be total 1800 newtons on both of these faces. I'm not really sure where that number came from, but that was in the previous result here. So yeah, so the only other thing that I've added here is a bolted connection. So I'll just delete this actually, and then we can go through the process of making it. So if you come into the connections, obviously we're gonna have a bolt that goes through the top of this part and screws into the actual spine. So you can come into the connections and choose a bolt. Default is going to be a standard bolt with a nut. So that would be like if you're bolting two kind of sheet metal parts together, where you would have access to the threads on either side of the component. Same thing, but with a counter bore. And then what we're going to be using is a standard bolt without a nut, or a screw, I suppose. That we don't define a nut anywhere on this. It's just we define that that face is going to be the area where the threads are in connection. Same thing with the counter bore. And then there's also a foundation bolt, which is you can model like a plane that is going to be your hypothetical foundation. So particularly if you're doing like cranes are a super good example, where cranes are like bolted to a foundation. So it's essentially like a bolt that goes into a fixed constraint, which is useful for some applications. So here we're just going to stick with a standard bolt with no nut. We select the edge where that bolt is going to be located, and then we can select the threaded face. This should already be set up to have bolt head diameter is 3/8 of an inch, and the actual bolt diameter is 1/4 of an inch. So this is a 1/4-20 bolt that we're simulating here. Material is alloy steel, that's fine. Some of the numbers that like McMaster has on their website seem a little bit high, but I guess they kind of make sense. They're certainly higher than the alloy steel material SolidWorks has defined, but we're not too worried about it here. We're not anywhere near the area where the bolt is going to be the thing that actually gets broken. This is aluminum, so the aluminum is going to deform well before the actual bolt would run into any issues. So last thing we can do is add a preload to the bolt. So bolt preload is a whole thing in itself. Essentially defines how much compressive strength you have in between the bolt and the parts that you're looking at. And usually you can use it to like set the torque spec for how far you have to tighten a bolt. The equation calculated isn't that weird. And there are a lot of calculators online for how to do it. It's basically just the proof strength of the bolt multiplied by the tensile stress area, which is some other formula that I don't know off the top of my head, of the bolt. And then multiplied, if you want to have the connection be kind of a reusable one where you might unbolt it and bolt it a lot, we're going to want to multiply that value by 0.75. It's going to be like, this is not ever going to change. You're never going to take this bolt out again. You can multiply by 0.89 or 0.9, depending on which source you look at. And that'll get you your axial preload on your bolt. And then from that, you can take like the pitch of your bolt and figure out what the actual torque value that you want to tighten to is. Now, simulating this, incidentally, if you go into the SolidWorks toolbox, which lets you add like standard bolts and stuff and washers and nuts and all that kind of stuff to your model, you can actually import those into the simulation when you run it, and then it will decide what the preload is going to be. Or you can take the bolt that you're going to be using and calculate some numbers based on that. So with this, it's kind of weird because I've calculated depending on which, so like my actual calculated values were like 2,000 pounds of compressive force. I found some calculators which were reporting like 1,000 pounds and below. Some calculators were reporting like 3,000 pounds compressive force. So I don't really know what's going on here, but I just set it to 1,000 pounds, which is our force here, which is what the key thing is. So this is a pretty simple model to analyze because the force acts directly opposed to a single bolt. So really you just want to make sure that the preload is more than the tensile forces that your bolt will have to be holding against, because what can happen is if your preload is less than the forces that you're pulling the parts apart with, then your bolt can just come loose. That's an area where vibrations will start to unscrew the bolt super quick. So yeah, in general, you just want to make sure that your preload is more than the forces that your bolt will be experiencing, so then it makes sure that the parts are held together super nicely. So 1,000 pounds isn't bad. This is 1,800 newtons, which is going to be like 500 to 600 pounds or something. So yeah. So that's our connection. That's our bolt connection. Again, we can create our mesh. I'm actually not going to, oh no, I will. Yeah, so we can create our mesh. We want to do that fine, but a little bit fine. And we'll run. And then it will say very high aspect ratio elements were detected in the current mesh. And you're like, what does that mean? What's going on here? I just want to press a mesh and get to my simulation. So a kind of quirk of how the FEA math works again is that the elements that you want to solve for should be as normally sized as possible. The ideal element is going to be a tetrahedron based on only equilateral triangles. But depending on the geometry you're looking at, oftentimes you're going to have to kind of stretch the element in different ways to get it to fit into the model you're looking at. And when you do that, you're going to lose some accuracy with your parts. So if SolidWorks detects that high aspect ratio elements, which just means the ratio, if you look at one of the triangles that makes up the side, the ratio between like the height of it and then another height, essentially. So if you have like a super tall triangle, the one height is going to be super tall, the other one's going to be pretty short. If that ratio is large enough, then it will throw you an error, ask you to show a mesh quality plot. In general, not all, it's sometimes perfectly okay to have high aspect ratio elements. But generally you want to avoid them, particularly for like the basic stuff that we're doing here. So it'll highlight you what the areas of interest are. So here we have some ones on the top, and these could probably be solved just by increasing the mesh density a little bit. Fit a few more meshes in here, they can be a little bit more regular. But you can see I have a little probe here, just pointing somewhere on the bottom of the part that shows the maximum. So up there, that's like 40. Aspect ratio is like 40. In general, I think like the consensus is that anything above 40 doesn't make sense. Some people like to say keep it below 20, which I tend to prefer. But this one, max, is 158, which is considerably larger than 40. So let's zoom in here and see what's going on. If you see, we have this very, very thin line right in this area where this is a face here, and you have to try and mesh that. If we go to the model, we can see the result. That's happening because we have two fillets that are very, 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 very close to touching. So it has to try and mesh between those, and because of the element size we've set, it essentially just breaks it up into like two very stretched out elements. One triangle goes here, the other triangle goes there, or four, I guess. And that's really bad. And that'll get you some weird results. So if you get that, you can just fix it by changing the size of the fillets. I just decrease the size of these a little bit. You can also increase them so there's no face between the two fillets, it's just a single edge. That's just something you might run into depending on the geometry of your model. And then if you mesh it again, that's a much better mesh in that area. So it won't give you the same error. So this is the same model. Another thing I haven't mentioned is mesh controls. So like I've said, the mesh size will determine how accurate your results are going to be. In general, a smaller mesh size is going to be a more accurate mesh. And sometimes there are areas where you know that there's going to be a stress concentration where you're going to want a smaller mesh. So you want to increase the density of the mesh in that area without increasing the density of the mesh everywhere, so that you can still solve pretty quickly, but you still get the resolution in the areas that you want. And so all you do is right-click this and click Apply Mesh Control, and then you can select the area of interest. It can be an edge, it can be a face, it can be a vertex also. I don't think I have any here, but it can be a vertex. Actually, no, it can't. Yeah, it can be a vertex. And then you can set the mesh density here. So this is 1.5 millimeters. I think the global mesh size is like 4 or 5 millimeters. So I've done that here on this edge because I know that where the bolt is going to be pulling against, there's going to be a stress concentration. So I want a little bit more resolution in that area. And you don't necessarily have to do this because, again, we're going to be using an adaptive method. I have it turned off here, but I did the adaptive earlier, I think. Oh no, sorry, I didn't. With this model, you can actually do an adaptive because p-adaptive solutions or solvers do not agree well with no penetration context. And h-adaptive will run, but it doesn't necessarily like the bolt connector that we're using. So what I did here was just a manual h-adaptive, again, doing the same kind of thing, going through, running it, looking at the results, writing it down, simplifying or making the mesh smaller, running it again, looking at the results, and it converged pretty nicely right here. So you can see this is a area of stress concentration, but not a singularity, which is nice. And looking at these stresses, this makes sense. Where so we're fixed here, so we're gonna have some stress in these arms here. Out here is not gonna really feel anything. You can look at the factor of safety. Min factor of safety is 3.3. I think like the run I did before this was like 3.4. The one I did before that was like also 3.4. So this was a nicely converged model. And rather than having like 10, I can put this to like 5, so we can actually see. We can't even see some gradient. Yeah, all the stress is mostly in this area with this run. Obviously, I neglected like these holes because that's just a little bit annoying to do. And for the study, we got a good sense that this part is well strong enough to be able to support the loads placed upon it. And yeah, so that's pretty much what I've got for FEA. Trying to figure out how to do models. It's at times it's more of an art than a science. Like the mesh quality is going to depend on a lot of things. Like we haven't even gotten to, there's also Jacobian quality that you're going to be looking at, which is some other thing I didn't really know. You just want to keep that like as low as possible. It's not necessarily a deal breaker, but particularly in the areas of interest, you want it to not be in the red. Not looking at the magnitude necessarily, but just the spread of the results. And there's a whole lot more you can get into, like composites, obviously one big thing that I've been trying to teach myself. Things other than linear static studies are going to be super powerful, depending on what you're trying to do. You can do submodeling. Like I said, that might actually help you in areas where you have stress concentrations. You can like solve the model and then cut out a circle around areas where you have a stress concentration here, and then solve it again, and in a much finer mesh, and make sure that those results are fine. But yeah, there's a lot to simulation.
Does SolidWorks have like fibers, like fibrous materials? Just wondering.
Okay. Are there any questions like more related to?
No. Okay.
Well, no.
Yeah.
I want to talk about that, but I just don't want to like get too far off track if people have questions about what we talked about. Does anyone have any other questions related to like the kind of linear static normal stuff that we talked about? Okay, seeing none. So SolidWorks has some capability to do composites. So let's just make a quick airframe here. And let's extrude it. Out like that, let's say 5 inches, 10 inches. So when we were doing the previous models, we meshed all of those. Well, also first of all, so SolidWorks does have materials that you can set in the part level for fiberglass and carbon fibers. The issue with those is that they don't have a lot of the material properties that you need, because carbon fibers and glass fibers are not linear. They're, well, first of all, they're not linear. They're also not homogeneous, whatever the word is. There's some word for it. So they have different responses to stress in different axes that you force upon them. So you can set this, and mostly you'll just get like the mass out of it will be the only useful thing. When you come into simulation, we'll just run a static here. I think usually you'd want to do a some kind of nonlinear study, but just for now. So I need to remember how to do this now. Okay, so you can come in here, and like I said, we've been doing all of this as 3D solid models. So you get 3D meshes, tetrahedral prisms, I don't know what they are. And then all the forces are solved between those meshes. There are also 2 optimizations you can make. One is turning the mesh into essentially a surface, so it's just a 2D mesh. And the other is turning it into a 1D mesh, which is used for like a beam. So generally where that's applicable, like let's say you're doing a like kind of scaffold structure, you don't need to know the exact 3D forces at every point in like a 20-foot long aluminum or steel pole
Right.
in 3D space. Really, you can just model it as a single beam, and the general forces will make sense. And when you do it, you can set some set some parameters like the thickness of it and all that kind of stuff. And that'll speed up the solve your model considerably, like many, many times. Because if you look at a 3D model, you're going to have millions and millions of elements, whereas a 2D model is not even hundreds of nodes, which are the points. So each element will maybe have, each 2D element will have like 10 nodes, which is just essentially like vertexes all around it. And then a 3D element will have, I guess, like 4 of those. So you have 40 nodes per element, of which there are millions if you're doing 3D. So SolidWorks offers simplifications in the form of turning it into a 1D beam that's just node line, node line, node line, or a 2D shell, which is same kind of thing. Like they're still elements, but they only have 3 nodes, and it's just a 2D mesh. There's no 3D aspect to it. So what you can do is, if you have a part like this, you can either, like this might be a good candidate for turning into a shell. Usually where they use is like sheet metal, where it's like bent sheet metal parts where it's pretty thin. So you don't really care about the stress distribution inside of it. You just care about the general forces that it's applying or it's withstanding. You can do that here. You can set it as either a thick or a thin piece. So it's like super, super thin sheet metal. You can just say it's thin. If it's a little bit thicker, you can do it as thick. Also, there's an option for composite modeling. So this is, it's a lot. And frankly, I don't really know that much about it. But so yeah, so right now this is set to the midplane of the body in question, which is pretty good. So you can apply all these different plies and tell the software their angles, and from that it will be able to get a sense of what the actual composite is going to do. It's very complex. I've watched a lot of hours on videos on it. I'm no closer to understanding exactly how to do it correctly, so I'm not going to go any farther than this and maybe like tell you something wrong, but yeah, so it does have composite capabilities. I think generally you might want to do like ANSYS or something else rather than SolidWorks for if you're doing complex stuff like this, or like I know Autodesk has a dedicated FEA tool for composites, which is probably a lot more powerful than the one SolidWorks has. But yeah.
Okay. Thank you.
Okay, any other questions? Getting close to the end here. You all set?
Thanks for running the workshop, Troy.
Thank you for coming.
Thank you so much.
Let's